So this is part 2 to solving solving exponential logarithmic equations. I don't like these strategies. Don't write them down. I forgot to delete those slides. I don't like those slides anymore. But these right here, you've already seen. In the last video, they were in the lower corners right here and right over here. There was 3, but here are the 2 most important. Okay, I'm trying to drive home this fact. The fact is that they have the same base. If they have the same base, you get to cross them out. They cancel each other out because they would be inverses of each other. See, for example, this one has a base a, this logarithm, and this a is also a base. Did you know that? He has an exponent of 1. Whenever they don't have an exponent, there's always an exponent of 1. So they have the same base, and if they have the same base, they cancel each other out because they're inverses. That's why you get the answer of 1. Over here, base A, they cancel each other out. And then over here, we have the same thing, except written with natural logs to try to show you guys how it can be written a different way. Natural log has base E, and that has an exponent of 1. Those would cancel out just like these ones cancel out up here because they have the same base. Again, natural log has base E, and this is base E, so they cancel each other out. That's why you get X. Okay, any questions about that? So let's see what it looks like when we put it into play with these logarithmic equations. Alright, check these dudes out. Now the very first thing you need to do is condense it so that there's 1 log. Once you get 1 log, then you can do the inverse operation to get rid of the log. I'm going to give you guys a chance to try to condense it without me doing it first. Okay, here we go. Now you first want to condense it. You want to write it so there's 1 logarithm. Let's do green first, then we'll do red. Christmas colors, yay! Okay. Now in order to condense this, we have to have nothing multiplying to the logarithm. But right here we have something multiplying to the logarithm. So we're going to take that guy and pop him up so that he is on the 7. So now you have log base 5 of x minus log base 5 of 7 raised to the 3rd power. Now if you have 2 logarithms that have the same base and you have a minus sign right there, that means you can do what with what's inside the logarithms? Divide. Notice I put the parentheses. You don't need them, but I like putting them there, especially when you're learning this for the first time. We have log base 5. Now which one goes on top, the x or the 7 to the 3rd? The x, because he was first. If you were to read this, he is first. So we have x divided by 7 raised to the 3rd. That's inside your logarithm, and that equals 0. How do I get rid of the log so that I can actually solve this? You can't divide by anything. What is the inverse of log base 5? Log base 5. It is raising it to the base 5. So we raise both sides to the base 5, and these will cancel out. What is 5 raised to the 0? It is uno. So we put uno right there. Then we have x divided by 7 raised to the 3rd power. Okay, now, still in my quest to get the x alone, what would I do next to get the x alone? Multiply. Do the inverse of division, because it's dividing. So we multiply it by 7 to the 3rd power, multiply the side by 7 to the 3rd power. So we get x equals, because these cancel out, whatever 7 to the 3rd power is. What is 7 to the 3rd power?
Yeah,
It's 49 times 7, yeah.
343.
343. Bam. Let's go into the next one so we can get down with our next examples. Now, for this one, we have again, the same bases in our logarithms, so we can write the logarithm once. But this time it says plus. What do we do when it says plus? We multiply what's inside. So we have x plus 2 times x minus 4. I'm going to use big old brackets to show that this stuff is inside of the log base 4. Now you can use big old parentheses, but big brackets are more fun to write. On the other side we have a 2. Now how do we get rid of this logarithm so we can finally solve our problem? Raise it to the base of 4. So we raise it to the base 4, peace out. And then we raise this side to the base 4. So what does the right side equal?
16.
16. The left side equals x plus 2 and x minus 4. Now if you do this, you're wrong. Okay? Don't do this. If you do this, if you say x plus 2 equals 16 and x minus 4 equals 16, that's wrong. That's not true. You can't do that. You are trying to use a 0 property when it doesn't equal 0. It equals 16. It has to equal 0 in order to use a 0 property. So how do we make that side equal 0? Yeah, we would subtract 16. But I can't do that yet because these are multiplying. So we'll have to multiply this stuff out and then subtract 16. So if I multiply it out, you get x squared minus 2x minus 8 equals 16. Then I subtract 16 from both sides. I would get x squared minus 2x. Wait, did I do something wrong? No, it's not plus 2x. No, because the negative 4 is more than the 2. So it's minus 2x and then minus 18. That's right. Okay, so I subtract 16 from both sides, so I get negative 24 equals 0. Ooh, please, please, please. Can I factor this bad boy? If I can't factor this bad boy, what do I have to use? You could use the quadratic formula. Okay? Or you can complete the square and go that way, but I wouldn't do that. I would use a quadratic formula. But can you factor it? Yes, you can. Oh, I picked a pretty one for you guys. Thank you, Mr. Patey. So x plus 4 and x minus 6, those multiply to give you that polynomial. Now you could take each of these and set them equal to 0. You could say x minus 6 equals 0 and x plus 4 equals 0. And so you get your answers to be 6 and negative 4. But you must check for extenuating solutions. How do you do that? You plug them in. What cannot be inside of a logarithm? A negative number. No, you're allowed to have a 0. Log of a... Wait, can you have a 0? No, you can't. You can't even have a 0. Oh, you can't have a 0. Yeah, because you can't raise something to the power to get 0, right? Like I can't raise 4 to a power to get 0. So you can't have 0 inside of here, and you can't have negative numbers.
Like after you add it?
After you plug in the numbers. So first thing you do is you plug in 6 to both of them. If I plug in 6 there, and if I plug in 6 there. Do I get a negative or a 0 in either of those? No, I don't. So 6, we're good. Okay, you're good, 6. What about negative 4 and negative 4? Oh, this one is that was a negative. Oh, this one's also wait. No, that one's also negative. It's negative 8. So negative 4 is our extenuating solution. I don't really know if I'm saying that right. I gotta double check my words here. So your only answer is x equals 6. Okay, try this. Now, I know when you guys first see this, you're going to think this. You're going to think, oh, I'll just take log base 4 of both sides. And I know this kind of looks ugly, but I'm just going to write it out and see what happens. So log base 4 of 8 raised to 3x. And then hopefully you did something like this. You know, you crossed out these because they have the same bases. They're inverse operations, which is why you did log base 4. And so, oh, and we can drop this 3x, right? Because it's an exponent. So I have 3x times log base 4 of 8. Then what would you do?
What? Would you find the log? You would do 4.
So let's say this. Let's say I want to raise this to the base 4. Well, it's not going to cancel out the log because this would have to go back up to an exponent. So, but then these would cancel out. But then you're going to raise this to the base 4. Now you're back where you started. Okay, so that doesn't work. What if I divide by x? Then I divide this side by x, and now I would get 3 minus 1 over x, right? Equals 3 times log base 4 of 8. Do you guys know what log base 4 of 8 is? That's not an easy one. You'd have to pop that into a calculator, huh? And you get this ugly decimal. Okay, see, this is not very clean. Now, it is possible, and I can show you guys how to do it. But there's another way to do it. And let me show you the other way. The other way is using manipulation. Now, this is the hardest thing for students to see for the very first time. But once you see it, you start going, oh, yeah, I can do that. Manipulation is this. Look at the 4 and the 8. Do they have a common base? They do have a common base. They both can have a base 2. 4 would be 2 raised to what power? It would be 2. And 8 would be 2 raised to what power? 3. So that's my 4 raised to the 3x minus 1. And this is my 8 raised to 3x. Ah, now things look a little nicer, a little prettier. Now, do you guys remember what to do when you guys have parenthesis exponents? What do you do with these to the inside exponents? Do you guys remember? Yeah, so we're going to take this, multiply it to the inside exponent, so we have 2 raised to the 6x minus 2. And on the right side, we have 2 raised to the what power? No? 9x. Yes. Okay. Now, Log base 2 both sides makes everything very nice, right? Log base 2. Log base 2. Peace out, peace out, peace out, peace out. So I'm left with 6x minus 2 equals 9x, which is way nicer than what we were doing before. Subtract 6x from both sides, I get 3x equals negative 2. X equals? Negative 2 over 3. So in this situation, I mean, that's why the answer was getting all ugly. The answer here is negative 2 over 3. What is negative 2 over 3 as a decimal?
0.6.
Negative 0.6666, right? It goes on forever. A non-terminating decimal, it's a repeating decimal, which would make the other way really difficult to solve. Now this one's not that bad. Once you know that trick, that manipulation trick, you can do this one no problem. Do they have the same base? Yeah, this one already has a 7. How would I write this one with the base 7? 7 to the negative 2, right? Because it was on the denominator, so it's a negative number. I do log base 7 on both sides, so I could cancel these dudes out. And I'm left with 3x equals negative 2, which is x equals negative 2 over 3. Ooh, how fancy. Same answer. All right, that's it.
Wait, I didn't finish.